Well, good morning, everyone, or good evening, good afternoon, wherever you come from. Welcome to the start of the third day of DVCon and the first of two panels for today. This panel is titled The Meeting of the SoC Verification Hidden Dragons. Back when I was a verification engineer many years ago, verification used to be considered to be the elephant in the room. But that was back in the days when the systems of yesteryear are perhaps the blocks of today. Maybe those elephants have now evolved and now they can breathe fire from their trunks. So when I asked Dave Kauf, the organizer of this panel, about the mention of dragons, he mentioned, or he talked about Game of Thrones and knights in shining armor slaying the dragons. I perhaps wonder if a better analogy, especially in these times of increasing violence, might be better thought about how we tame and befriend the dragons. Who knows, perhaps they can help us find and eliminate the bugs. But before we get started, a few mechanics. So first of all, this is your panel, and we really want to have your questions. However, having conducted several of these virtual panels in the past, I know that we won't be able to get to all of your questions. There are many questions that are posed during these panels. So firstly, I do apologize if we don't get to yours. We're going to do three things to try and address them. First, we will answer some of them in the session, of course. Second, I've asked the organizers to preserve the Q&A associated with this panel, and that's important, the Q&A. So if you're going to pose questions, please put them in the Q&A, not the chat. So we'll collect all of those, and those questions will be given to the panelists after the event. And if they want to provide written answers to any of them, I will find a way to collate them and make them available. And third, DVCon has this social app, gather.town, something like that, where people can talk about the panel after we've finished. I suggest that anyone who wishes to discuss the panel goes to the red social area, and there they can continue the discussion. Unfortunately, I can't be there, but feel free to have a discussion amongst yourselves. So, to tame the dragon, we have a panel of experts that comprise 3 users and a vendor. The users are Mike Chin of Intel, Balachandran Rajendran, Dell EMC, and Tai Karibay, Mythic AI. And on the vendor side, Adnan Hamid, Brecker Verification Systems. Firstly, I'd like to get each of them to very briefly introduce themselves, and then we'll get into the real content of this panel. Let's start with Mike.
Hi, my name's Mike Chin. I am a validation engineer at Intel, focused on validation content for IP validation and pre-silicon, as well as reusable content down to the SoC in pre and post and manufacturing.
Thanks, Mike. Bala.
Hi, I'm Bala Rajendran, CTO for semiconductor design vertical within Unstructured Data Solutions Group. I play more like an advisory role within this.
Thanks, Bala. Tai.
Oh, and yet adding the useless senior manager viewpoint as the VP of engineering at Mythic. We have a unique challenge of managing the development of an analog and digital system, and so that has some interesting verification issues. I think I like the dragon analogy here, primarily because I think the shape of a dragon is relevant. They typically have kind of small heads, and you see that first, and you go, okay, it breathes fire, it has teeth, maybe not so bad. And then they have a huge body, and you're going, oh my God, what do we do with that? And then the tail goes on forever. And so I think verification is exactly like that.
I think I'll stick with the notion of the fire-breathing dragon, and we can have the flames coming out of his trunk. That gives you an even longer lead into verification. So on the vendor side, we have Adnan.
Hello, everyone. So I'm Adnan Hamid. I'm founder and CTO at Brecker. And my interests lay in IP verification, SoC verification, and firmware verification, and how to reuse content across all those layers.
So thanks, guys. So most of the verification methodologies in use today, and for that matter, the tools, were designed primarily for block level verification. So my first question to you is, how does block level verification differ from SoC level verification? And let's start with the users on that. We can do the same order we did the intros, Mike.
Well, I look at a breadth versus depth problem, right? In our space in IP validation, it very much is a depth problem. We want to validate all the nooks and crannies within the IP, within the block. But then as we scale it out to the SoC, we really don't care so much about having to get that same depth. We rely on the interfaces that we do the integration. And as long as those are held, now we're looking more broadly across the entire SoC. What are those SoC functions like system PM or memory access? Those are the things that we would look at and want to validate. So it really is it's a very orthogonal problem when you go from IP over to SoC.
Yeah, I think that's a good analogy, and I also believe that there is a little bit of parallelism in a sense that a lot of the methodologies, even within the block, there are either it's a pre-verified IP, ARM IP that could come from, you have some confidence, but there could be some internal IP within the group or within different organizations within the company. Then there are different methodologies on what we want to actually accomplish at the SoC level. The thing that Mike talked about at the SoC level, yes, it's a more a breadth problem, which is true. But at some cases, you want to go dig deeper because some of those problems could traverse back on the breadth side.
Hi.
Yeah. So you're still playing with the dragon analogy. The verification at the IP level, we're building single plates of armor. We're covering this spot. We're trying to make sure that spot cannot be pierced. The SoC, now we put all of these together, and just as in classical days, the weaknesses are at the seams. That's where somebody's going to get through and get you. And so, I spend most of my concern about verification, not worrying too much about the IP and trusting the super engineers we have doing that, but trying to understand where are the assumptions at the seams that are going to allow for a bug to get through. And that's the great fear that I live with, that especially with very complex SoCs that have many interfaces, many different kinds of interfaces.
So Adnan, what attempts have been made to redefine tooling for SoC verification?
My favorite topic. So I think picking up with the conversation of IP versus SoC and going to your question, Brian, I think the landscape is shifting. I think we've been talking about it for many years, but I think I finally see the shift in the users. I think first, the IPs are getting complex enough that our tried and tested UVM flows are no longer scaling. So we need to do more for that, right? So what are we doing on that front for the tooling? We are introducing the system UVM initiative, which is to bring UVM style constructs to the UVM guys that are familiar to them, but bring them the power of what portable stimulus can do. Okay. At the SoC level, more and more I see that I completely agree with Mike, right, about the depth versus breadth thing, that at the SoC level, we're not interested in getting into all the details of the IP. But we got to test the IP. We can't not test it. And in fact, what we got to do is test that different IPs work well together. And if I'm the integration guy, integration team, I don't have time to go learn what each of these IPs do. So this is a huge problem in the industry. And then finally, today, firmware is pushed way back till after integration, after the device is up. And that's way too late, right? Software takes 3 times as long as hardware. So more and more, I'm seeing hunger for being able to test that firmware on the IP unit benches, which is one of the things that we're enabling with the system UVM initiative.
So in many cases, when we get to the SoC level, It really is a combination of hardware and software and workloads and having to put together these end-to-end scenarios. So, how important is it that we either look at real software or synthetic workloads or synthetic software? What is the scope of SoC verification in terms of how close we have to be to the eventual system? Who wants to start?
I'll start on that. Right. I think at Intel, we've seen that it's not sufficient for us to just look at use cases, at production use cases, because the minute that you have a use case that falls out of what you've tested, a bug's going to be found, right? Absolutely the problem. But I think there's a larger problem as well, because then if we say, okay, production use cases are not sufficient, so we must go with synthetic. The space of our validation in that synthetic space across multiple blocks, and we talk about cross IP flows, talk about interactions between IPs, the complexity grows huge. So we want to do synthetic. I believe that in order to do good engineering, that's what we want to go focus on. But what we really need to do is be able to have some sort of method to help focus us on what is important, like Ty's analogy before. Where are those cracks in the armor? We have to be able to identify those so we can go and focus our synthetic validation on those.
Yeah, I guess follow up. Thank you. The challenge we have, perhaps uniquely on this panel, is as a startup, is a fundamental scarcity of simulation cycles. We have a relatively limited number of licenses, computes, machines, whatever, and time and engineers. So the focus is absolutely critical. How do we, the most important thing we do every day is figure out, okay, where are we going to put our limited resource? So I agree completely that we have to have that synthetic implementation, because for a lot of our workloads, we don't have enough compute to simulate a real workload, for very long, maybe a few frames. That's about it. And so there's a high value put on at the architecture definition level, specifying a architectural simplicity that can be addressed synthetically, such that there isn't a exponentially growing space. And so it really starts at that product definition level to make sure that it can be verified in a reasonable amount of time for us.
Want to add anything, Bala?
No, I think Adnan has something he raised his hand.
Bala fell asleep. I do, of course. So first, I'm 100% with Mike that production workloads don't do it, right? In general, software protects hardware, and real life cases get into corners only rarely. So we need synthetic. But I greatly agree with Ty's point about the search spaces are enormous. Right? And the strategy we've been going down at Brecker with using planning algorithms to generate test cases, whether the algorithm is fed by PSS or system UVM or C++ languages detail. Planning algorithms inherently want to reason about the entire space. And when you do all the math, the search space is freaking enormous, right? And that's just the sequential coverage. You combine that with the concurrency coverage and all the ways things can interleave, and you're looking at these numbers that are basically useless, right? Numbers like 10 to 100 tests just are not useful numbers, right? But at least we're getting to the point where we can do math from them. We can start doing managerial decisions on what of that space must be covered in simulation, what must be covered in emulation, and what must we do in silicon, right? And I think there's a general sense that industry is starting to understand this, because if you look at the last Wilson research thing that we did, right? That Mentor Siemens did, excuse me. the biggest care about of everybody is how do I get enough test content for my design? So this is becoming, it's been a huge problem and it's getting bigger.
So I am going to actually pull in a question from the audience here, since it is kind of very pertinent to where we are. It says, can you touch on exactly what you mean by synthetic validation? Mike, maybe you can provide a little more information on that.
Yeah, synthetic validation, for what I'm aware of, or what I'm familiar with, are internal workloads that we design, that we use to test. It's not a production flow. It's not something you'd find, say, in a Windows driver or a Linux driver. It's more open-ended and is typically we validate to the spec of what that IP or that block is supporting.
Okay, thanks.
Right.
Now,
let me add one
go ahead,
aspect.
yes.
There is again, as a unique aspect of a startup, especially a startup not working in a software compatible space. Our software tools, of course, are being created in parallel with the silicon, usually later than the silicon. So even if we wanted to run a test case of real workload to validate the hardware, often the real workload doesn't exist yet. And so that synthetic case is something that the architects and the verification team and the software team put together to say, here's the types of data, the data rates, the control flow insertions that we expect in the workload. And then, we validate to that to some extent with some randomness injected, and then we tape out and pray.
thanks.
I'll concur on Ty's this thing, which is even on our GPU development that we did is emulating that on the emulator with the software component built, and we also see that as a synthetic thing because actual real production will that be going into a mobile phone and somebody using it. So we are not there yet, but we do it. Android gets booted up and other applications that you run on it. We see that as a part of a synthetic test as well.
Now, a little earlier, Ty, you kind of mentioned about the, not having enough simulation cycles. And, part of that would seem as though because we're stuck doing SoC verification on RTL models, are there ways in which abstraction could help us solve this problem?
That's a fair question. And we do use architectural abstractions primarily to validate software, where you're not as concerned about timing hazards. That's critical to enable the software development to proceed in parallel and separate from the hardware development. That doesn't obviate the need for cycle accurate simulation of the actual flops and not really the gates, but some representation of the gates that are going to be implemented in the silicon. And really the only accelerator we have today is a hardware box, right? And I think that becomes our functional limitation. We can use a bunch of computes to do Verilog simulation for some period of time, but at some point we have to get on the box and try to run a big chunk of stuff.
I think I would agree, right? I mean, I think NVIDIA's flow is well announced that they have the top level architectural models that are sort of end-to-end single models, and they break it down into F models that are modeling each block in the design. And they test at that level, and that's great, right? Make sure that you have your foundations around the blocks correct. But in general, especially for most SoCs, I'm not seeing that the abstract models have enough fidelity to go do the real verification that we need to do. And that's a problem, right? We should have it, but we don't.
And then who should verify that abstract model? How good is that model?
Well, that actually has a straight answer, right? Or at least I can answer that in a straight manner, which is just as we are going to test software on the abstract model, like and Ty was talking about, we should be testing that abstract model with the same content that we eventually plan to move to the real design, right? Once you think about test content as being portable and plentiful, right? So another question in the chat about that you should bring up, Brian. But then we should use it everywhere, right? So test the A model, test the F model, then go test each of the RTL blocks, test the system, bring in firmware, blah, blah, blah. I mean, why not start testing firmware with randomized test content on the abstract model? These things are absolutely possible today, but we haven't got them. It's not been done.
Okay, so another audience question here. What are your views regarding the future of formal verification when AI ML technology is emerging quickly in the industry? Do we really need both to achieve final verification goals?
You run that question again? I didn't quite catch the question.
Do we need both formal and I guess simulation and emulation, given what AI and ML can do? I'm not quite sure that they're mutually exclusive, but I guess there are two parts here. Do we need both simulation and formal? And secondarily, is AI ML going to influence the way that we do verification?
Oh, good gracious me. Okay, before I take that apart, let's tell everybody. I think everybody else should go first. No?
Anyone using formal?
You're ready, Adnan, so you should go.
Of course I'm ready. Okay, so I adore formal. Formal is beautiful. And if we could do all our testing with formal, I would be the first one to go after it. If somebody could show me how to do formal on silicon, I would be really excited, right? Because silicon has electrical issues that we can never even get in simulation. So I think there, and besides, formal is severely capacity limited in relation to what we're trying to build, right? Formal keeps getting better, but our designs keep getting bigger faster than formal gets better. So we definitely need dynamic testing. So that in turn means we need dynamic test generation. And that in turn gets us to this capacity problem, this huge search space where we're throwing darts into the space. And now we've got to pick good darts because we get only a few samples in a very, very large space. And this is the problem that we have to deal with. And on the topic of ML, so I'm in the business of using AI planning algorithms to generate test cases. This is very different than ML, right? AI ML. ML is basically fancy statistics. Planning algorithms are basically fancy rules. And the problem with verification is it's not good enough to be 90%, 98% correct. You got to be 100% correct. And that's the trouble with the statistical approach.
Yeah, I think there's an interesting future that we hopefully will see is can machine learning techniques help guide effectively guide randomized testing, with the Brecker tools or other tools, and get to, I guess, the 98% level faster. That does still, as you point out, leaves the 2%. What do we do? That still has to be covered with more rigorous techniques. With formal, unfortunately, I've always felt that formal was what you do when you hire a PhD and did his thesis in formal, and only wants to do that from now on. You say, okay, well, I guess here, take this block and play with it for 2 years. But it's been otherwise it's been challenging to deploy in the real world.
Manish Pandey yesterday in the keynote had some really good data there, right? He showed, if I recall, 20% of bugs in pre-silicon are found in formal. 65% are found using simulation or emulation, some sort of functional execution. But we still have bug escapes. And if we go towards the larger question that we've been asking or trying to address, is how do we find those bugs? I think it's going to be a combination of all of these technologies, all of these methodologies that really helps us. AI ML may be something we can apply towards trying to find those corner cases and then generating the tests to cover them, right? And that's a huge win in terms of getting us those higher quality bugs that we need to find. So I think it's in the end of the day, it's going to be a mix of everything. Just how that mix plays out is going to be an interesting journey to watch.
And it's going to be an individual organizational choice on what mix of what percentages they want to use. And I don't agree with Adnan where he says ML is expected to its statistical model, and if it's not going to give me 100% accuracy, then I don't want it. I see it differently. It's more like a tool. If it's able to assist the human in the loop, the verification engineer who's actually doing it, if it's going to assist him do a better design, figure out which test he's going to use, then it's a good tool set. It's going to add value. It's going to make Ty's job much easier in terms of, hey, I have limited resources, I have so many licenses, I need to do that. If ML can assist, even with some level of accuracy, it's able to move the curve to the left, which is in terms of time, TTR, then it's a good plus.
If I can find 10% more bugs using machine learning, right, then that's a bigger win for me. Yeah. And I'll go solve the remaining 10% that's even harder to find with a different approach.
And let me walk myself back a little bit because I do agree with you guys, right? It's applying the right technique to the right problem. Using ML to guide other test generation schemes, using ML to guide where you should look for debug. These things can be close and they're still very useful, right? What I don't see is, hey, let's go feed ML a bunch of existing simulation traces, and from that infer what we think the test cases will be, because what will happen is 98% of them will be good, 2% will be bad. Engineers will debug them and they will get tired of debugging false failures. So, so that's a little bit where I'm coming from, right? That we got to have generalistic understanding of research spaces, but guiding, yes, I'm with you.
You know, an application I would love to see, and maybe there's somebody out there, you know, in the research community, looking at this, is more of a RTL quality analysis based on an AI approach, where we could say, hey, check this RTL and point out to us where it is unnecessarily or unexpectedly complex that we can't tell. And I think you could create training sets, or synthetic training sets that would say, look, here's a state machine that talks to another state machine that talks to another state machine that drives a bus or something, and say, that's bad. You should not do that. And then can an ML agent find that in the RTL, and crossing from IP to IP, where perhaps the design engineers would never have thought, oh, I didn't realize that was going to go from my block to that block and be used that way. And that's the type of scene coverage that would be really interesting to see if we could accelerate, because then we would say, oh, either one, change the design, or two, okay, let's really put a dude on that and test the heck out of that interface and make sure that we exercise the space. So those are the types of things that I think I would be one very welcome, but it might actually be possible.
And what you're suggesting, what you're suggesting would have huge value, right? It's really about identifying where is the most complexity that we fail to acknowledge or we fail to understand, right? And a objective tool can very well help us to understand that.
Wait, you two are advocating that engineers will write simple code? Won't it revolt on principle? I'm with you guys.
I'm only a manager anymore. The fact that I don't actually do anything real anymore means that I can say these things.
Hey, I'm with you. I run around in my company beating up people to write simple code.
Yes. Anyway, so I think here's an interesting kind of follow-on question that digs into that a little deeper. Considering the state space is large, what would a typical ratio for SoC verification be when considering simulation versus emulation today? And I guess we really should put in post-silicon into there as well. And how do you see this evolving going forward?
So as the guy who worries about the state spaces and doing the math on them, I think the answers actually drop out very clearly. Okay. So we can all imagine that there's enormous state space. And if I put some algebra around it, we can talk about combinatorial coverage, have certain things happen at the same time. We We can talk about sequential coverage. Have we seen things happen in the orders we care about? And we can talk about concurrent coverage. Have we seen those sequences stack against each other in all the concurrency cases we care about? A thing that planning algorithms like to do that you mentioned in the last panel I was on with you, Brian, is it likes to start with the outcome and work backwards to test scenarios. So if you have very limited simulation, you of course want to start with testing every possible outcome, which essentially means what it amounts to is, have we done every use case? Have we sent inputs from every input to every result? And then as you get more capacity, say emulation post-silicon, then you go off and let the tool make a bushier search, go try more ways to reach each of those outcomes. So I think these questions have very straight answers when you can see the search space. But well, let's make no bones about the fact that we're solving very difficult problems, right? I like to say, in a project, in your project, you will, in the lifetime of the project, you will run maybe 10 to the 7, 10 to the 8 test cases. And your search space is in the range of 10 to the 50. So you get to do 10 to the 8 test cases on a space of 10 to the 50, which is coverage of exactly 0%, right? It's 10 to the minus 42 or whatever it works out to be. And we got to guarantee no failure. And this is what we do.
That's why I say it's a miracle it works at all, right?
Exactly.
I'll tell my boss anyway. You should be happy it works at all. So, since I'm not smart enough to understand all the math, I think the practical side is really the limitation I look at is, again, from a limitation of resource and time and usability, we're typically going to use simulation for months or years. Typically, you don't have a solid enough design to put on emulation until relatively late in the design cycle. And so you're maybe in the last 3 months of the design, you're saying, okay, let's do some DFT oriented stuff, some power analysis oriented stuff, some firmware bring up stuff, some initial workload simulations. Now the total cycles run on emulation may in the end be quite a bit larger, even in just the 3 months, than it was for all of the simulation you did for 2 years. But the time and the engineer time put into it is always going to be a small percentage today versus what we invest into a typical Verilog simulation.
So Ty, would you say that simulation to emulation, is it an order of magnitude increase in terms of emulation tests that you're running compared to simulation?
Cycles, yes, but time is actually in the inverse, wall time.
Yeah, I'm a fan of. Yeah, I was about to say I'm a fan of emulators. So even in Ty's case, you don't have to wait until late stage. You could run it in a simulation acceleration mode until you use the emulators much more effectively as well. And that ratio is not going to be fixed for a SoC because it's going to depend on what kind of SoC. What is it actually doing? If it's an AI chip, just going to do an audio listening and it's going to detect that, hey, some security or something is broken in the factory, then it's going to do a different set of thing. Then maybe just the simulation cycles will be higher. But if it's going to do video and a lot more interconnects and a lot more IP in that chip, then we need a lot more emulation piece. We'll go into that.
I guess part of that says, that where are the bugs being found? Are you finding an order of magnitude more bugs in emulation? Are the bugs that you're finding, are they in the short runs or the long runs? Are they, as Adnan was talking about, are they in the combinatorial or the sequential or the concurrent space? Has anyone been keeping track of where the bugs are lying?
I'll go first. In that context, I think yesterday's Manish Pandey's keynotes were very good, and Mike brought that up as well. One of the things that it talks about, hey, we did 20%, I don't remember the numbers, but like 20% informal, 65% in simulation, and then some 10% in hardware. A lot of these bugs, so I think that's not the right way to look at where the bugs, depending on number of bugs are found in a particular state, doesn't mean that it's a good thing. I'll flip the conversation a little bit differently, which is that depending on when we do it, because depending on when we do it and the whole continuous integration, continuous development methodology, is that you're going to find the bugs. If a lot of the bugs are found in the early stages, this is where formal and static verification comes in. Yes, you will have a bigger chunk of data set bugs pointing to that, and later on the emulation side, the IP is almost good enough. At that point, you might find less bugs. The intent, I think I would see it a little bit differently in terms of not just go by where you find those bugs.
That's very well said, Bala. Yeah, for us, the simulation tools are simply much more friendly for debug. So if you're finding a lot of bugs on emulation, that's a practical limit on just the use case. But we do find more is perhaps bugs in software. Still product bugs for us because our product is a hardware software product. Those are bugs that likely we could only have found on the emulator because we wouldn't have been able to run the larger case in simulation. So it's perhaps correlated to the level of abstraction you're operating at. Hopefully in simulation, I think as Bala pointed out, then you're finding all of the IP bugs, most of the SoC bugs, and then you may find a few SoC bugs in emulation, but probably most of your software bugs, at least pre-silicon.
And I think, Brian, when I heard your question, the question a little bit rang false for me, okay? I spent a lot of my time walking the halls of my customers' offices, these days the virtual halls, working with them. And I really think, I feel safe saying that the rate at which we find bugs is gated by how quickly we can come up with the test content more than anything else. So if things were found in latent hardware, it was because we never got around to testing that. If an IP bug was found, say in silicon, it was because we didn't get around to doing that content. The reason we're finding firmware bugs in emulation and not simulation is we haven't enabled the firmware team to run on IP simulation, and that's due to all the accoutrements firmware needs to run, needs to be able to execute it all. But if we can solve that problem, then you can test your firmware on the IP unit bench, and there's a whole class of bugs we could remove that take up time in emulation today. And I think those technologies are becoming available now.
But I mean, and I agree with you, Adnan, but I think there's maybe a practical counterpoint. But Ty said he's running simulation for years. If as a software developer, if somebody developing a firmware, if I'm going to be running a simulation, a lot of simulations just to test out my software, I need a faster platform. Right? I need something that is more responsive to me. And that's why emulation is a nicer niche for the software developers than simulation, because the amount of time it takes is you could run a simulation for 3 weeks before you get the result you're looking for.
So Mike, maybe my point didn't come out. First, I completely agree with you. Big fan of emulation. Please don't hear that I don't think we should do that. What I am saying, actually using terminology that I learned from you, Mike, is there's the business logic for the firmware that is very specific to an IP, the lowest level routines. And most, maybe this is true, but many of the bugs that we find in software have to do with the poor software guy screwing up his interpretation of what the spec said. It wasn't that he decoded it wrong. It wasn't there's a plumb logic error in the software. It's just he got it wrong. Mm-hmm. Now, if we can get that low-level firmware routine to run on some kind of verification OS, as you say, Mike, and have that verification OS be able to go down to, say, UVM unit bench, and test out that guy, provide the firmware with whatever scheduling, memory allocation interrupts it needs. It needs doing this is kind of like getting a heart to beat without the body around it, right? So can you give it something lightweight enough that can run in simulation and still run the firmware, which you can, which we are in fact doing with some of your coworkers, Mike, right? So this lets us go make sure that firmware is operating on hardware correctly at the lowest level, because the fact is higher levels of firmware go into an OS, and that it's kind of there, it's kind of working, right? So we screw up stupid stuff in software. Mostly because we don't know how to write specifications, right?
I'm going to combine a couple of questions here. So there was a question about whether better visualization tools would help, and talking about visualization in terms of complexity, coverage holes, all of that kind of stuff. And the question implied that companies are having to develop some of their own tools to fill in some of the needs. And I think there's a bigger question here in the fact that I would presume that different kinds of SoCs see different verification challenges. So for example, mobile chips going to be very different than data center CPUs, AI accelerators. So how much should we be relying on the EDA vendors to provide exactly what we need for verification versus how much is there always going to be left for the user companies to work out what do we need to solve our specific problem?
That's a great question. I think on the visualization side, I see it more as an enabling function. There's big, huge companies that make their business today helping people visualize data, SaaS companies, right? Visualize their data flow, the variations. And I think, and I've started to see a couple of players in the verification space starting to provide infrastructure that is similar, that enables people to rapidly create dashboards, to visualize verification results. We are happy customers of one, and we'd love to see more tool agnostic, I guess, not vendor specific solutions offered in that space, and that say, okay, we'll look at all your regression results and help you build up a visualization of this or that, right? So, but every verification team and verification team lead wants to think that they know their specific product best and what is the most important thing, and that goes to your, what's the difference between products question, part of the question. For a lot of people working on chips similar to mine, our chips are highly iterated. Each processing element is relatively complex, but then we have a lot of them, and really the checking of how those things play together, less complex, hopefully, until you get to the full use case scenario and running full software. So we would be more interested in a lot of processing tile down type metrics, whereas a mobile SoC, like I used to do, has lots of use cases that are cross IP, where you have to really understand how is this IP feeding that IP, feeding that IP, controlling that IP. And they would have a very different desire and interest to get information from system level and IP level regressions and combine them. So I would look for flexibility in the tools, and then to be able to adapt to the variety of challenges that we face across the industry.
Anyone else?
Stunned silence.
You guys will all laugh at me because I'm going to say what I always say. So visualization. I adore visualization. I think human beings are visual animals. I think we think about our problems visually. And my soapbox forever has been, we've got to reduce our verification problems to flowcharts, right? This is what I always say. People always kid me for it, right? So flowcharts, we should be drawing PowerPoint flowcharts, right? We shouldn't be writing piles and piles of code. That's the input side. And on the coverage side, when you start thinking about sequential, so we already have visualization for common deferral coverage, right? Tools like Birdie go to a lot of effort to try to give this to us. You can do the same for sequential coverage. You can do the same for concurrency coverage, and it's beautiful. And then it gets super scary, right? When you're actually faced with your 10 to the 4 sample set on a space of 10 to the 50 or whatever the name might be, the data looks horrible. And then you wonder what you really want to show and show your customers, right? So there are issues.
But I think that's the problem, right? We can go from simple visualization. And by the way, I believe visualization is a very admirable direction that we should go, because like Adnan said, we're all visual animals, right? We're very visually stimulated. But the amount of time that we are going to spend in trying to find the right visualization that takes out that 10 to the 4 or the whatever the size of the coverage space is going to be huge. And what is the return that we get upon that investment? Are we better? I guess I would ask the question, maybe going back to the ML discussion that we had earlier. For the amount of effort that I would put into doing visualization, would I be better served in spending that effort into having a tool that can identify for me the complexity that I would have been looking for from the visualization work that I do? Right.
Fair. I think arguably they might be actually linked, though. If you can formulate the data or format the data in a way that could be visualized, it can also be processed by standard ML techniques.
Yep.
So I think there's linkage there that another questioner pointed out, that if you could have open, unencrypted, standard, outputs from the tools, it opens up this type of creativity in how we approach and post-process results using any form of a tool, be it visualization or machine learning.
Absolutely, right. If we took our RTL today, we put it in some sort of a graph representation, we can run graph-based ML AI algorithms on top of that, right? And you could even take that same representation and just apply a standard visualization to it. I guess the question that I'm asking is, when we if we were to go down that route, and we still can't identify, or we still have a problem identifying the individual trees in that very large forest, right? And those trees being the problems. That's where I would want a tool for me that can help identify that for me without much more effort on my part.
Okay.
For ML, are our data sets large enough in relation to the complexity of the design? I wonder.
Combining another couple of questions here. So there was a question, Ty, that you had mentioned that you were short on compute resources. And Adnan, you were talking about we're really only constrained by how quickly we can develop new stimuli sets to go in. And I know a favorite topic of yours, Bala, is kind of regression. It's sort of, how do we balance the amount of compute resource simulation time that we spend on trying to find new problems with the growing size of regression suites that are consuming even more simulation resources to make sure that the last change we put in didn't break something?
I'll go on the green verification, that term coined by you, Brian.
Hey.
And then I'll hand over the rest of the stuff to Adnan and others. That I'm actually excited about a lot of SoC companies and as well as EDA design companies moving to more on the cloud, which is good, because in the past, when they're doing on-prem, all this cost layer was abstracted to them. To them, they were like, hey, I have infinite amount of cores, I have licenses, CAD team will take care of it. I don't have to worry. I don't have to design my verification suite that way, my verification applied. But as soon as they move to a cloud, now they have, every time they run something, they're going to see a cost to it. So they'll have a much better, and I'm hoping that with this model, they'll slowly be a little bit more conscious, and with that, they'll become much better at doing what they want to do, and they'll optimize it. And verification engineers are awesome at optimizing, so I'm sure they'll optimize it and make it more greener by that path.
Fair. I mean, that certainly is a limitation for us, and we do track the cost, but really it is the resource. And in the end, especially today, the tightest resource is the engineers. The recruiting environment today is insane. And and we're all fighting for the same superstars who can make a big difference in our teams. And you know, without the people, you're tempted to think you can run 1 million jobs instead of 100,000 and get to the end goal. And you know, clearly that's not the case, but the temptation is there. So, you know, I've read several articles recently that, you know, the world is short, you know, many tens of thousands or hundreds of thousands of IC designers in the next several years. And certainly we're seeing that play out in our industry, and it is you know, limiting the ability to move products forward.
So I think this starts to bring out what I very much feel. Now, it's very much my personal opinions, and you guys can beat me up for it. Okay, so now I'm going out on a limb for you, but Brian, this is what I'm seeing, and I'm not going to name any customers because none of this is good, right? This is all very dark underbelly stuff. Yes, we're short people. Why are we short people? Because we are asking to go write these reams and reams and reams of test cases because we don't have enough test cases. Yes, we need these really bright guys. Why do we need really bright guys? Because run-of-the-mill B-grade person won't think of all the cases because we haven't given them good algebras to go figure out all the cases, right? We depend on them to be smart. We don't give them a calculus that says, here's how you figure out what everything else is, right? So this ties into my graph-based thing. And if we do it visually, then you don't have anywhere to run, right? But these are not the real issues. Yes, we use simulation. We have to use simulation tie. It is economic, it is debuggable, they're all these kind of things. But as the IPs are getting bigger, these sims are running for 2, 3, 4, 6 hours. Now, as a brilliant DV engineer, if each experiment takes 6 hours, you're in this business of trying to say, okay, I'm going to work on about 3 things at a time. Sort of kick off the test for 1, go work on the item 2, kick that off, work on item 3. Tomorrow I'll come back and item 1 will be ready. We are human beings. We don't stack swap efficiently. This stuff is just absolutely killing productivity, and I don't think we are aware of this, right? So I think, Bala, one of the things that I think we're going to have to go to more simulation acceleration like you're advocating. But I think it has a large part of it needs to be driven by the human faculty, right? Nobody talks about the fact that engineers sit around waiting for 6 hours of a simulation, right? Go do something else in between, can't you? Can't you think about 10 things in parallel?
Yes, very long coffee break.
Yes.
I think that I want to touch upon a few things. I think I just saw an announcement that Verifitter got acquired by Cadence. It's a good announcement, and we used it. And in my previous role at Verifitter, did some really cool things. In our Ty talked about some of the CI, continuous CI/CD mechanism in which there's some automation built. So what we did in my previous role is that it looks at the whole perforce check-in that goes in. If a test bench has failed, automatically traces back to that particular change in the code list that failed, and then figures out who that person has actually checked in and assigns that ticket automated way. So all of that actually really helps. Very small thing, but those are the small steps that are repeated 10,000 times in a particular chip. So if you could automate any of those, I kind of see it as whether you should go for mosquitoes or go for a shark. I'd rather go for a mosquito because there are a lot of them. It kills a lot more people on the planet compared to a shark. So these are those small mosquitoes that we should go after and improve productivity.
Anybody else?
Well, maybe speak to Adnan's point. And there was a question about tool scalability and Moore's law, right? If we take what Adnan's saying, and I believe what Adnan's saying is correct, and I can't tell you how many times I'm working till the middle of the night, right? We are trying to scale humans in order to scale our designs and meet the challenges of our designs. But we do have a fundamental challenge because the tools have a finite limit in terms of what they can actually do and how they can perform, right? Simulation is going to take 6 hours. It will always take 6 hours unless we come up with some sort of breakthrough. And I think that's where we are unfortunately not measuring the cost, which is a human cost, of trying to tackle more and more complex designs. This is a big problem, right?
Yeah, Mike. And first, I'll attest to Mike being up to the middle of the night, and second, some of this has low-hanging fruit answers that we're just not thinking about. This is boring stuff. So we are used to, in UVM, we're used to dynamic test generation. But that means every experiment has to run the full simulation. Can we move to a point where we can generate the test, look at it without running the simulation, and say, okay, this is the set of things it's going to do. Does that make sense to me when I eyeball it? Can we visualize it? And then submit it. So I think there's low-hanging fruit that can also be improved, that we're just not thinking about what we're asking our engineers to do, right? We're asking our DV engineers. They're, in fact, the IP DV engineer is the only person in the entire company who really understands what IP does, right? I like to say the architect comes up with a system architecture, understands about 80% of what it needs to do. Each IP gets handed off to the IP engineers, then designers, they design it, and they understand about 80% of what they designed. So by the time DV gets it, it's 64% understood. It's the DV guy's job to understand the remaining, what's it, 36%, to understand 100%. Well, that's great. That's what we hired them for. Okay, this is their job, to understand all the cases. On top of this, we want them to learn all kinds of different languages, all kinds of different tools, and build these very complicated environments. We're completely overloading them. So.
Yep, I want to touch upon Mike's thing. Why does simulation have to be 6 hours?
Our tools today are, they're only as fast as they are, right? This kind of the point is, if we can get a technological leap forward, then yeah, 6 hours can reduce down to 3, right?
I think you're right, Mike. It's always going to be 6 hours because that's the pain point, and we're going to increase the scope of complexity to the point where that's where we draw a simulation boundary. And as Adonis pointed out, and you as well, our IP level blocks just keep growing in complexity, and they tend to grow to complexity until they run for about 4 to 6 hours, because that's about all we're willing to tolerate, or else we would break it up into some level of hierarchy that we could address independently.
Taking that a little further, so what is the dragon? Is it that the simulation limit of what we can do? Is it the number of scenarios that we can run through that put those blocks together? It's of what is it that's effectively going to limit how far we can take the SoC. Ty, you talked about how far we can take the block. How far can we take the SoC, and what's the verification limiter going to be?
It's not a dragon, it's a hydra.
Yeah, absolutely. I'll let
Go ahead, Ty, please.
So for me, and I'll cycle back to something I referred to earlier, I think what we'll see is a greater and greater emphasis that needs to be placed on architecture and specification, and more formal verification, more formal specification that may enable more formal verification at the higher levels of any SoC, so that doing the IP verification correctly will lead to has a greater probability of leading to a successful SoC, because we won't be able to, as complexity continues to increase, verify, these SoCs in traditional methods. Same way we don't verify boards in traditional methods.
And I think, Ty, you're touching on what more and more I'm growing to believe. Our biggest problem is us. We build these organizations that have sort of walls between them. We have these IP guys who are told, you go verify the IP, that's your job. When the integration guys come to them for help, it's kind of like an annoyance, right? Because we haven't motivated the IP guys to do this. And I'm more thinking about the larger companies. And the firmware fellows are off somewhere on a different planet and don't talk to either of these first two groups. And I think those walls have to be broken down. And what's the thing called? The verification gap is the name of what's the title of our talk here? I mean, I think there are the gaps, which is to break down the walls, be thinking in terms of how can we get the IP content reused in SoC. Somebody has a question out of, hey, can we take these very useful sequences we write in UVM and make them available to firmware? Yes, we should, and we're starting to do that work. Can we get the firmware and the UVM guys to decide what the API should be for IP? But these are big organizational issues where it requires bringing the right people to the table and them willing to talk to each other.
I'd like to finish my participation in this, as we come to a close, by agreeing with Adnan. When I was his customer, I was always happy to agree that he was the problem.
Oh boy. As you say, Ty, we are out of time at this point. So we did actually manage to get through most of the questions. So good job, guys. I want to thank all of them, and I know we can't kind of give them a clap that anyone but can hear, but hopefully you'll be doing that to yourselves. And thanks very much, guys. Very interesting panel, and we'll see you anon. Bye for now.
It's fine.